All right, so this is kind of day one, part two video. We are going to focus on just the applications and the bearing style questions that were at the end of 8.1, because these can get pretty exciting. So we really, let's see, I think we need to start where they continue talking about how to add two vectors together and get a resultant vector. I think that's where I left off. All right, so when you add two vectors together, you get a resultant vector, and the two vectors, one vector should affect the other. So the application questions that we see a lot of in our PreCalc class and in our trig classes and in our physics classes are like airplanes and aircraft being blown by wind. So there's two methods. Triangular method, which is tip to tail, and you end up creating usually a law of cosines question. And then the parallelogram method, which is just like brute force geometry method, and then we're going to use the components. I don't have strong feelings over either method. Turns out it really would help if I knew how to draw to do any one of the methods. Bad news for everybody today, I can't draw, so we're going to do the best we can. This, if we were in class, I would tell you guys just to watch me do this question and help me out, so when I label something wrong, you can help me with this. Drawing it is kind of half the battle. So, we have an airplane that's flying at an airspeed of 310 knots. We can label that on the picture at a heading of 50 degrees. So they did a true bearing of 50 degrees. So right here is 50 degrees, and this is not 50. This is 310 knots for a magnitude. I should probably label this as 50 degrees though. And then the wind, and this is confusing because the 78 knot wind, which I'll draw 78 right here, it's blowing, and this is the key word here, this preposition, from a true heading of 125. So you pretend like you're going to draw a vector of bearing 125, which would be down here. And then instead of going outwards like a normal bearing would travel, because it's from that bearing, it's actually pointing towards that one. All right. So I have to make a decision as to how I want to approach this vector question, whether I want to approach it like a physics kid or a math kid. And we'll teach you both. I'll do this one like you would in physics class, because that's what some of you are in right now, and maybe that'll make you comfortable. All right, so this vector is heading in that direction, and what's going to happen is this airplane's trajectory is going to kind of get pushed this way. So what I'm going to do is I'm actually going to clone this guy, and I'm going to create a parallel vector, assuming I can grab it, up here. Okay. So they are parallel to each other, so we have some geometry going on. And remember, this was 125 degrees all the way down to this vector. So if I am curious about angles, like this angle right here, for instance, this is, okay, what did I just say, 125? So this is 35 degrees. And then this angle right here is 40 degrees because of the how far away from 90 complement theorem. And this total angle here is 75 degrees. Now, remember that alternate interior angles business? That means this angle right here is also 75 degrees. So here's what's going on. I have a new, what we call resultant vector, that connects where the plane was to where the plane is now going to be. And that's what's really going on. So I need to figure out the new speed of the airplane and also the bearing that I can associate with his new position, because he was moved by the wind. So what I have going on here is I have a triangle, and this blue line is still a magnitude of 78, and it's a little hard to tell what's going on because it's all messed up together, but this triangle, I think I can use law of cosines to find x. So we could set up 310 squared plus 78 squared minus 2 times 310 times 78 times the cosine of 75. And that's going to equal x once I square root it. And once I type all that into my calculator through the art of somebody else already doing this for me. Oh, wrong paper. Somebody got 299.4. Probably would have been quicker just to type. So that is the new speed of the aircraft. That's the magnitude. Now they want the bearing. So in that triangle, I know it's 50 degrees from the vertical to this red line. I wonder if I look at just the triangle's angle and I found this angle right here. So I could now set up a law of sines question, because now I know this guy is 299.4. I can set up law of sines. So we'll say the sine is 75 over 299.4. equals, now I want this angle, so let's set it up across from 78. So the sine of, you can use any variable you want. I'm just going to use x, if that's all right. Sine of x, it's a bad variable to use. Oh well. Over 78. And then when I go to solve for x, I'm going to cross multiply sine 75 times 78 divided by this, and then inverse sine at the last minute. And I just found that x is totally an answer. What is it? 14.6 degrees. Now, that's not my bearing. Remember, that was the angle in the, that's 14.6 degrees. Oh my gosh. 14.6 degrees. That's this little red angle here. So what I'm going to do now is the entire bearing of the original plane, it was 50 degrees off of true north. So, oh, for Pete's sake. I'm going to take that 50 degrees and then subtract this 14.6 we just found. And then that's 35.4 degrees, I think. Oh my gosh, I should be able to do that, right? Yeah, I did it. And that is our bearing. So you can say a true bearing of 35.4 degrees, and the new magnitude of 299.4 knots. So that was, from what I understand, the method that you guys use in physics, and there's absolutely nothing wrong with doing it that way. In fact, I think that's the way I was taught at one point in my life, and that's kind of the way I continue to do it. Oh, but before we move on to the next question, you got to be real careful about how they word this. So that one we just did said from a bearing of 125 degrees, so that's blowing from the end of the what used to be the vector towards the aircraft, usually in these questions. Now, if they switch the word and they say been blowing at a bearing, then it's going in the opposite direction. It's going away. So you have to be really, and that's the way we would naturally draw it, so you just got to be careful. So, oh man, there's a nice picture there I could have used. My bad. Okay. Lovely. We're going to skip the swimming question for the sake of time, and here for this helicopter question, I'm going to show you the two separate methods, and then you decide. So, for the first method, I'm going to use the components, and the components I'm referring to are your horizontal and vertical components, right? So we're going to have two different vectors that are working together, and then we're going to add those vectors' components together. So once I can find these four pieces, it'll be easy peasy, and a little bit of, frankly, geometry at that point. It's not even trig. A helicopter is moving 15 degrees northeast with a velocity of 52. All right, I should draw that. So here's our helicopter, moving like so. And 52 is its magnitude. I'll label at another time because my picture is going to get messy. This is, what, 15 degrees? So I can find the components of the helicopter pretty quickly. I can do 52 times the cosine of 15, and then 52 times the sine of 15, which I think I have, pretty sure I have these answers somewhere. Maybe not. I guess not. Get my trusty calculator. Or not. Time out. Alright, so the horizontal component is 50.2 and the vertical component is 13.5. I'm just rounding to the 10th place if we're all okay with that. I'm going to keep that in mind, and then I'm going to look at the wind. So the wind is a 30 kilometer per hour wind at a bearing of 250. So I'm going to do that one in blue. So true bearing at 250 would start, from north and then travel, it's 180, this is 270, so back up a little bit. So this is the bearing, roughly, but it says from. So this is that weird one where it's not pointing out this way, it's pointing from that direction. So this is like, Mrs. Hoffbauer always draws a little windy cloud. He's blowing like that, right? Totally, nailed it. Okay, so the arrow's going like this. So here's what I do. I take that bearing and I just like randomly drew a length of the bearing. It doesn't necessarily stop at the origin like I inclined it to do. So what I'm going to do is I'm going to draw kind of over this. I'm going to draw like that. So this angle right here is 20 degrees, right? Because this is 250 and this is 270. So this angle here is 70 degrees. So what that tells me is this angle is 70 degrees and this angle from here to here is 20. So when I look at that blue vector and I think about his angle he makes with the positive x-axis, the angle I'm going to be using is this 20-degree angle right here. Sorry, that's really confusing with the colors, isn't it? So his vertical and horizontal components are going to be, what was his magnitude again? 30, right? So 30 times the cosine of 20, and then 30 times the sine of 20. So when I typed those in my calculator, I think I did 28.2 and 10.3. So here's what's going on. Our resulting vector ends up being, and I'm having a real hard time drawing it, but in the middle of the two this time. So when we use this method, this is the, I don't know how to describe it. I'm not going to bother. I'm not going to even bother describing it at this point. So I forgot what they called this. Well, we're calling it the component method. They called it something else on the other screen, but whatever. What we're going to need to do now for this red vector is we're going to need to add these two together. So, new vector is, when I add those together, 78.4, comma, 23.8. And if you can envision me, like, creating, oh geez, I just made it so much worse, didn't I? Okay. Creating this new red vector, and then thinking about, you know, what are his horizontal and vertical components. That's what I'm asking you, right? So I know his horizontal component is 78.4, his vertical component is 23.8, and then you need to find the magnitude. We're about to find that because we can do Pythagorean Theorem. So 78.4 squared plus 23.8 squared, and I think I did this. Yep, I got 81.9. So that is the new magnitude of our helicopter. He's going 81.9 kilometers per hour, which, cool. Makes sense, I guess. All right, so then we have to find our new bearing. Our bearing has changed. That angle in that red triangle, I think we could do a little inverse trig, right? We could find this angle in the red triangle by doing the inverse tan of 23.8 over 78.4. This I haven't typed in yet, so let me try that. Quit. Inverse tan of 23.8 divided by 78.4, and you get 16.9-ish. So that's this angle here, and that would be fine for a bearing. You could say a bearing of 16.9 degrees from the horizontal. You don't always have to do the off of true north business that your trig book made you do. We could have. It's just 90 minus 16.9. It's not the end of the world. All right. So again, if you have some different decimals, you might be rounding it a little different. So let's do, I like that method. I think mostly because it didn't require me to draw super well, and I could still figure it out. I like algebra components and formulas. I think they make me very happy. This method, this is the one you guys do in physics, and there's nothing wrong with this method. It's just, it's very difficult for poor Mrs. Abruzza to figure out. Okay. This question is, let's see, I need to draw it. I cannot tell you how many times I've had to draw this. All right. I wonder if there's a nice drawing over here. Nope. All right. Let's try again. So we already kind of had it drawn, right? I had this guy. And it was, what, a 52? And then I had this guy. That was a 30. And we had some angles. We'll worry about the angles in a minute. But here's what I'm going to do. I'm going to copy, clone, I guess, that. I'm going to move it, hopefully, over, or not. This is the tip to tail method. So I'm taking, I'm supposed to be taking this and moving it up here to where that other tip was. Or no, tail, excuse me. I always get this confused, I don't know why. So I'm not really going to consider this vector anymore. I'm going to look at his twin vector over here. And then I've created this triangle, which is very hard to look at. So what I'm going to do is I'm going to draw a kind of skewed, not that I can draw a good triangle anyways, a skewed triangle over here that's a little easier to read. Maybe. And I'm going to label it again over here. And then I'm going to superimpose a coordinate plane so I can look at angles. I'm going to do all my messy work over here. I'm going to make my clean work up here. Alright, so just like the last two questions ago, I'm going to need to find this angle somehow. So here's what we have, guys. We have a coordinate plane right here. If only I could figure out that angle. Let's see what we know. Alright, I know this is 20 degrees right here. I know this is 70 degrees. I know that this is 15 degrees. Okay, here's what I want you to think about. We have this and this line that are parallel to each other. And then this green thing is cutting through it like a transversal, right? So that tells me that we have some alternate interior angles to work with, I think. Oh gosh, I made my problem really gross now. My bad. Here's what I know. This is 70 degrees, which means this is 70 degrees. I don't know if I need that, but I'll mark that. Well, that's confusing. I'm going to erase that because there's too many lines going on. Okay. So easy to read, Mrs. Brusso. All right. The angle that I know is, oh, I got this. This is 90, right? Right here. This is 15. And this is 70. So this entire angle from here to here is 175 degrees. Well, this angle and this angle are alternate interior angles, so that angle is 175 degrees. That was incredibly gross. This is why I don't really like this method, because my pictures are never nice enough to come up with that missing angle. Alright, let's find our magnitude using law of cosines. So x squared equals 52 squared plus 30 squared minus 2 times 52 times 30 times cosine of 175. And then when you remember you got to square root this one, you get, surprise, surprise, 81.9, which is the same magnitude that we got using the other method. So I know we've done something right at least. And now they want the bearing. So for the law of cosines questions, it's best if you now go through and you find law of sines. I don't know if this is the best way for you guys. It's just the best way for me, so I'm going to do that. If I could figure out this angle right here, and I know the bearing from here originally, I think I can figure it out. Because remember, guys, this was, I have the wrong bearing. The bearing on the green guy, wasn't that 50? Well, we'll come back to that. Okay. Once I can figure out phi, if I take, remember this was 15 degrees down here? So my bearing is going to be 15 plus this phi thing that I'm about to find. All right. Law of sines to find phi. Remember, guys, we know this. This is 81.9. So we have sine of 175 over 81.9 equals sine of phi, or x or whatever, over 30. Your book likes to use phi. Greek letter. Good old Greek letters. All right. Multiplying sine of 175 times 30 divided by 81.9 and then inverse sine at the very end. We just found out that phi is 1.8, teeny tiny angle. So my bearing would be off of the horizontal if I want to frame it that way. So my bearing of 16.8 degrees from the horizontal. So at the very last minute you have to decide how you want to describe your bearing, and it could be from true north if you really just love doing it that way, or you can always go off horizontal. Whatever is easier for you. Okay. Sorry for the messy picture. I hope yours look better.